So this is another one of the example structures that I'd like for everyone to be able to do, and you will likely see this on one of your tests. And this is what I call a bar, the horizontal bar there, that's supported with a strut. Now, when I say that this kind of structure may be on your exam, if I put the structure and I draw it slightly differently, maybe the horizontal bar goes like this, and the strut is just a vertical bar, I consider that the same kind of problem. If I take this bar and put the strut underneath of it, that's the same problem. Okay. If I take the force at the end and I put it off at an angle, or I put it up, that's the same kind of problem. So the statics on all those types of problems work the same way. So I'm just going to go through one example, and I encourage you to do this on your own and change things up a little bit and work through the problem a couple different ways. But in this problem, we have a pin reaction here, and we have a pin here. Let's call this maybe point A and this point B. And this bar right here is pinned at A, and it's pinned up to this bar here. That makes it a two-force member. There are no other connections in between. A two-force member means that the line of action of the force that is in the bar 1 is directed along that axis of the bar. So I probably need some dimensions here. So let's just make up a few dimensions. And let's use feet units. So maybe this is 6 feet from here to here, maybe 4 feet from there to there, and another 4 feet to the end. Now there's a couple ways to work these types of problems. One way is to give you the numbers for the forces that are on the structure. The other is to give you the allowable stresses, or the failure stresses and safety factors. Just to make things simple for this example, let's just put in a number here. Maybe this is 2,000 pounds. And we want to find maybe the pin reactions at A and B and the force in bar 1. So the first thing we want to do is to draw an overall free body diagram of the structure. Now here's where I see a lot of people mess this kind of problem up. If I want the force in bar 1, the free body diagram that is the easiest for me to work with is if I draw a free body diagram of the horizontal bar, and I put this force F1 off at the angle that I'm going to call theta, which is the same angle here in this picture that I'll indicate as theta. I have a pin at B, so I have a vertical and a horizontal reaction I'll call Bx and By, and here's my 2,000 pound applied force. So if I want to find the force F1, if I do the summation of moments about B, notice how I'm putting my sign convention for my directions of rotation. I have minus 2,000 times 8. And here I'm going to have the sine component of F1. So I'm going to have F1 sine theta times the distance of 4 feet, and let's see, that would be in the positive sense of rotation, so that's going to be plus right here, then equal to 0 for equilibrium. So I want to solve that for F1. First I need to figure out what that angle is, though. If I look at this picture, this being a right angle, the tangent of the angle theta is equal to the opposite side over the adjacent side. 6 divided by 4, let me see what that is. It's not one I know off the top of my head. That would be 56.3 degrees. So F1 is going to be equal to, moving this to the other side, is a positive 2,000 now, times 8, divided by 4, and the sine of 56.3 degrees. I've got 4,807. to 3 significant digits. Let's call this 4810 pounds. All right, now if I wanted the stress in bar number 1, then I would take the force in bar number 1 divided by the cross-sectional area bar 1 and so forth. Now here's where I see people mess up. Instead of drawing this free body diagram, they will draw a free body diagram that looks like this picture, where I have a pin reaction here, and then they'll draw in a pin reaction up here. And if that's point A, maybe this is AX and this is AY. While this is a free body diagram that is accurate, it's not very helpful, because when you go to try to work this problem, you end up with what looks like four unknowns. You only have 3 equations of statics that you can use in this kind of problem. Summation of forces in the x, summation of forces in y, and summation of moments about a point. The thing that people miss when they draw this free body diagram this way is that these 2 reactions have to have a resultant force that goes down the direction of F1. There's an extra equation, a constraint equation, among those reactions, AX and AY, and the force in bar number 1. So while you can do that, I don't recommend it. So let me put a big X through this free body diagram. It's a good free body diagram, but it's just not useful. Okay, so try to avoid falling in that trap. Okay, so what things could be different? Like I said, the bar could be underneath, the bar could be vertical. The forces could be at different angles. Now, if I wanted to find the shear stress at pin B, let's talk about how to do that. I would need to first find Bx and By, so let's go ahead and find those. If I would do the summation of forces in the x direction, I would have Bx minus F1 cosine, I'll call it theta, equal to 0. In this case, since I know what F1 is, I can directly solve for Bx. Let's see, theta is 56.3 degrees. So I get negative 2670 pounds when I round it up to 3 significant digits. All right, if I want the summation of forces in the y direction, I'm going to have By, I'm going to have plus F1 sine theta minus 2000 is equal to 0. Since I know what F1 and theta are, I can solve for By. So let me do that. I'll have the 2000 to the other side. And then I'm going to take F1, going to multiply it by the sine of 56.3 degrees and subtract it from 2000. And I end up with minus 2,000 pounds. So those reactions really both go in the opposite directions from what I have assumed. Okay, so now if I want the shearing stress at pin B, okay, that's going to be the square root of the sum of the squares of Bx and By, and divide by the area in shear. If the pin is in single shear, it's pi over 4 times the diameter squared of the pin. If it's in double shear, it's 2 pi over 4 times the diameter of the pin squared. If I wanted the shearing stress at pin A, I could do it this way if I wanted to. AX squared plus AY squared over the area and shear of the pin. But remember, these two have to be the resultant F1, so we can just as easily write this as F1 divided by the area and shear. All right, so again, I'd encourage you to put in your own numbers, change the geometry up a little bit, take my picture, rotate it 90 degrees, and make it look a little different, but the statics will be the same, and work a few examples out so that you're practiced before you get into the exam.